Linear Programming. Introduction. Many applications in mathematics involve systems of inequalities or equations. In this chapter, we shall apply the systems of linear inequalities and equations to solve some real-life problems. A furniture dealer deals in only two items, tables and chairs. He has 50,000 rupees to invest and has storage space of at most 60 pieces. A table costs 2,500 rupees and a chair costs 500 rupees. He estimates that from the sale of one table he can make a profit of 250 rupees and that from the sale of one chair a profit of 75 rupees. He wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming that he can sell all the items he buys. The type of problems which seek to maximize or minimize profit or cost from a general class of problems called optimization problems. Thus, an optimization problem may involve finding maximum profit, minimum cost, or minimum use of resources, etc. In this chapter, we shall study some linear programming problems and their solutions by graphical method only, though there are many other methods also to solve such problems.
Linear programming. Let us begin our discussion with the above example of a furniture dealer, which will further lead to the mathematical formulation of a problem in two variables. In this example, we observe, first, the dealer can invest his money in buying tables or chairs or combination thereof. Further, he would earn different profits by the following different investment strategies. Second, there are certain overriding conditions or constraints, that is, his investment is limited to a maximum of rupees 50,000 and so his storage space, which is for a maximum of 60 pieces. Suppose he decides to buy tables only and no chairs, so he can buy 50,000 divided by 2,500, that is 20 tables. His profit in this case will be rupees 250 into 20, that is rupees 5,000. Suppose he chooses to buy chairs only and no tables. With his capital of rupees 50,000, he can buy 50,000 divided by 500, that is 100 chairs, but he can store only 60 pieces. Therefore, he is forced to buy only 60 chairs, which will give him a total profit of rupees 60 into 75, that is rupees 4,500. There are many other possibilities. For instance, he may choose to buy 10 tables and 50 chairs as he can store only 60 pieces. Total profit in this case would be rupees 10 into 250 plus 50 into 75, that is rupees 6,250, and so on. We thus find that the dealer can invest his money in different ways and he would earn different profits by the following different investment strategies. Now, the problem is, how should he invest his money in order to get maximum profit? To answer this question, let us try to formulate the problem mathematically.
Mathematical formulation of the problem. Let x be the number of tables and y be the number of chairs that the dealer buys. Obviously, x and y must be non-negative, that is, x is greater than or equal to 0, y is greater than or equal to 0. Non-negative constraints. The dealer is constrained by the maximum amount he can invest. Here it is rupees 50,000, and by the maximum number of items he can store. Here it is 60. Stated mathematically, Z is equal to AX plus BY. 2500X plus 500Y is lesser than or equal to 50,000. Investment constraint, or 5x plus y is lesser than or equal to 100. Equation 3. And x plus y is lesser than or equal to 60. Storage constraint. Equation 4. The dealer wants to invest in such a way so as to maximize his profit. Say Z, which stated as a function of x, and y is given by Z is equal to 250x plus 75y, called objective function. Equation 5. Mathematically, the given problems now reduces to maximize. Z is equal to 250x plus 75y. Subject to the constraints, 5x plus y is lesser than or equal to 100, x plus y is lesser than or equal to 60, where x is greater than or equal to 0 and y is greater than or equal to 0. So, we have to maximize the linear function z subject to certain condition determined by a set of linear inequalities with variables as non-negative. There are also some other problems where we have to minimize a linear function subject to certain conditions determined by a set of linear inequalities with variables as non-negative. Such problems are called linear programming problems.
Thus, a linear programming problem is one that is concerned with finding the opening value, maximum or minimum value of a linear function called objective function of several variables, say x and y, subject to the conditions that the variables are non-negative and satisfy a set of linear inequalities called linear constraints. The term linear implies that all the mathematical relations used in the problem are linear relations, while the term programming refers to the method of determining a particular program or a plan of action. We now formally define some terms which have been used above, which we shall be using in the linear programming problems.
Graphical method. Let us refer to the problem of investment in tables and charts discussed in section. We will now solve this problem graphically. Let us graph the constraints stated as linear inequalities. 5x plus y is lesser than or equal to 100. Equation 1. X plus y is lesser than or equal to 60. Equation 2. X is greater than or equal to 0. Equation 3. Y is greater than or equal to 0. Equation 4. The graph of this system, that is the shaded region, consists of the points common to all half planes determined by the inequalities 1 to 4. Figure. Each point in this region represents a feasible choice open to the dealer for investing in tables and shares. The region therefore is called the feasible region for the problem. Every point of this region is called a feasible solution to the problem.
Now, we see that every point in the feasible region OABC satisfies all the constraints as given in 1 to 4, and since there are infinitely many points, it is not evident function z equal to 250x plus 75y. To handle this situation, we use the following theorems which are fundamental in solving linear programming problems.
Theorem 1. Let R be the feasible region, that is the convex polygon for a linear programming problem, and let Z is equal to ax plus by be the objective function. When Z has an optimal value, maximum or minimum, where the variables x and y are subject to constraints described by linear inequalities. This optimal value must occur at a corner point, vertex, of the feasible region. Theorem 2. Let R be the feasible region for a linear programming problem, and let Z is equal to ax plus by the objective function. If R is bounded, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at a corner point vertex of R.
Theorem 2. The corner points vertices of the bounded feasible region are O, A, B and C, and it is easy to find their coordinates as 0, 0, 20, 0, 10, 50 and 0, 60 respectively. Let us now compute the values of Z at these points. We have the values as given below. We observe that the maximum profit to the dealer results from the investment strategy 10, 50, that is, buying 10 tables and 50 chairs. This method of solving linear programming problem is referred as corner point method. The method comprises of the following steps. 1. Find the feasible region of the linear programming problem and determine its corner point vertices either by inspection or by solving the two equations of the lines intersecting at that point. 2. Evaluate the objective function z equal to ax plus by at each corner point. Let m and m respectively denote the largest and smallest values of these points. 3. First, when the feasible region is bounded, m and m are the maximum and minimum values of z. Second, in case the feasible region is unbounded, we have 4. A. M is the maximum value of z. If the open half plane determined by the ax plus by greater than m has no point in common with the feasible region, otherwise z has no maximum value. B. Similarly, m is the minimum value of z. If the open half plane determined by ax plus by lesser than m has no point in common with the feasible region, otherwise z has no minimum value.
Example: solve the following linear programming problem graphically. Minimize z is equal to 200x plus 500y. Equation 1. Subject to the constraints, x plus 2y is greater than or equal to 10. Equation 2. 3x plus 4y is lesser than or equal to 24. Equation 3. X is greater than or equal to 0 and y is greater than or equal to 0. Equation 4. Solution. The shaded region in the figure is the feasible region ABC determined by the system of constraints equation 2 to 4, which is bounded. The coordinates of corner points A, B and C are 0, 5, 4, 3 and 0, 6 respectively. Now, we evaluate z is equal to 200x plus 500y at these points. Hence, minimum value z is 2300 attained at the point 4, 3.
Example. Solve the following problem graphically. Minimize and maximize z equal to 3x plus 9y. 1. Subject to the constraints x plus 3y lesser than or equal to 60, equation 2. X plus y greater than or equal to 10, equation 3. X lesser than or equal to y, equation 4. X greater than or equal to 0, y greater than or equal to 0, equation 5. Solution. First of all, let us graph the feasible region of the system of linear inequalities 2 to 5. The feasible region ABCD is shown in the figure. Note that the region is bounded. The coordinates of the corner points A, B, C and D are 0, 10, 5, 5, 15, 15 and 0, 20 respectively. We now find the minimum and maximum value of z. From the table, we find that the minimum value of z is 60 at the point B 5, 5 of the feasible region. The maximum value of z on the feasible region occurs at the two corner points C 15, 15 and D 0, 20 and it is 180 in each case. Different types of linear programming problems are listed below. 1. Manufacturing problems. In these problems, we determine the number of units of different products which should be produced and sold by a firm when each product requires a fixed manpower, machine hours, labor hour per unit of the product, warehouse space per unit of the output, etc. in order to make maximum profit. Second, diet problems. In these problems, we determine the amount of different kinds of constituents, nutrients, which should be included in a diet so as to minimize the cost of the desired diet such that it contains a certain minimum amount of each constituent or nutrients. Third, transportation problems. In these problems, we determine a transportation schedule in order to find the cheapest way of transporting a product from plants or factories situated at different locations to different markets.
There are two factories located, one at place P and other at place Q. From these locations, a certain commodity is to be delivered to each of the three depots situated at A, B and C. The weekly requirements of the depots are respectively 5, 5 and 4 units of the commodity, while the production capacity of the factories at P and Q are respectively 8 and 6 units. How many units should be transported from each factory to each depot in order that the transportation cost is minimum? What will be the minimum transportation cost? Solution. The problem can be explained diagrammatically as from the factory at P to the depots at A and B respectively. Then 8 minus X minus Y units will be transported to a depot at C. Why? Hence, we have X is greater than or equal to 0, Y is greater than or equal to 0 and 8 minus X minus Y is greater than or equal to 0. That is, X is greater than or equal to 0, Y is greater than or equal to 0 and X plus Y is lesser than or equal to 8. Now, the weekly requirement of the depot at A is 5 units of the commodity. Since X units are transported from the factory at P, remaining 5 minus X units need to be transported from the factory at Q. Obviously, 5 minus X is greater than or equal to 0. That is, X is lesser than or equal to 5. Similarly, 5 minus Y and 6 minus into 5 minus X plus 5 minus Y is equal to X plus Y minus 4 units are to be transported from the factory at Q to the depots at B and C respectively. Thus, 5 minus Y is greater than or equal to 0. X plus Y minus 4 is greater than or equal to 0. That is, Y is lesser than or equal to 5. X plus Y is greater than or equal to 4. Total transportation cost Z is given by Z is equal to 160X plus 100Y plus 100 into 5 minus X plus 120 into 5 minus Y plus 100 into X plus Y minus 4 plus 150 into 8 minus X minus Y is equal to 10 into X minus 7Y plus 190. Therefore, the problem reduces to minimize Z is equal to 10 into X minus 7Y plus 190. Subject to the constraints, X is greater than or equal to 0, Y is greater than or equal to 0. Equation 1. X plus Y is lesser than or equal to 8. Equation 2. X is lesser than or equal to 5. Equation 3. Y is lesser than nor equal to 5. Equation 4. And X plus Y is greater than or equal to 4. Equation 5. The shaded region A, B, C, D, E, F represented by the constraints 1 to 5 is the feasible region. Observe that the feasible region is bounded. The coordinates of the corner points of the feasible region are 0, 4, 0, 5, 3, 5, 5, 3, 5, 0 and 4, 0. Let us evaluate Z at these points. From the table, we see that the minimum value of Z is 1550 at the point 0, 5. Hence, the optimal transportation strategy will be to deliver 0, 5 and 3 unit from the factory at P and 5, 0 and 1 units from the factory at Q to the depots at A, B and C respectively. Corresponding to this strategy, the transportation cost would be minimum, that is rupees 1550.